Hello, welcome to another video from lean6sigma.net. This is Jorge Rodriguez. I am a master black belt, passionate about operational excellence. I work for lean6sigma.net, and with us, you can learn more about Lean Six Sigma reliability and other tools. We provide consulting and certification services. Please join our channel by linking the button below so that you can be in the loop for more videos about operational excellence, Lean Six Sigma, and continuous improvement in general. Today we have prepared a video to teach you how to calculate sample size specifically for a two-sample t-test. We're going to see the case of equal variance. A quick refresher, a t-test is a statistical method used to determine whether a sample mean significantly differs from a known target or hypothesized population mean. The key components of a two-sample t-test are, of course, the data. We need to formulate a hypothesis. Right here is the null hypothesis, where we state that the sample mean from one population is the same as the sample mean from another population. And the alternative hypothesis is that they're not equal. When we formulate it in this fashion, we're talking about a two-tailed test. In addition, we need to set up what our type 1 error is. That is also known as alpha, and it is or represents the probability of rejecting the null when in fact is true. We also need to understand what the beta value is, also known as the type 2 error, and the difference that I am trying to detect is the minimum detectable difference between the means, and we can see that value being called here delta. Our assumptions are going to be that the data is normally distributed, observations are independent, and of course equal variance is the topic at hand. So what is the process to determine this sample size if I am interested in executing this two-sample t-test? If the means are not equal, then we are concerned about making the wrong decision and failing to reject the null. In other words, accepting the null when in fact it was actually false. So our ability to make the right decision is going to depend on how big or small is the true differences of mean, and then there is going to be a relationship with the sample size in determining that particular ability. That's why this is very important to be done prior to actually collecting data, so that we know that we have the right power for detecting this difference. And that brings me to this other concept that we're writing here. Power is defined as 1 minus beta, where beta is the probability of type 2 error. In other words, is the probability of not rejecting the null when it's not true. Power can be understood as the ability of the t-test to detect a difference, delta, if it is not 0. And typical powers are 80% or 90%, but you can use any value in between as you would like. And remember, there's always a relationship with the sample size. We just defined that alpha is also known as the type 1 error, or the probability to reject the null hypothesis when it is true. In addition, to be able to calculate the sample size, we're going to need to know what the standard deviation is. So we can use some historical data for this, or collect some data initially with a very small sample size to sort of estimate what the standard deviation would be that we would use for our sample size determination. But never forget that we're assuming here that these standard deviations for population 1 and population 2 are going to be the same, because we're in the case of equal variances. There are three methods that we're going to show you in this video. The first method, we're going to do this manually using a formula. You're going to see that the results are going to be very similar, but there will be slight differences. But not something to be concerned about. The second method is using a published operating curve. This is a concept where we always plot the beta value against some standardized difference, and there are different curves for sample size. So all we have to do here is find the observation, so the intersection. So we have some formulas that were going to allow us to use this method. You can get the operating curve by going into Google and saying operating curve for a certain alpha level. In this case, we have 5%, and write something like 2 sample t-tests. You will see them immediately. So we're going to show you how to use this. And the third method is using a statistical software such as Minitab, RStudio, Jump, Sigma Excel, or SAS. In our example here, we're going to show you how to do this using Minitab, which is a very common tool in companies that use Lean Six Sigma. Now, if you're dealing with unequal variances, or you suspect that the variances will be different, then the methods that I'm showing you are not going to work, because the calculation has to be done through an statistical software, given that the math is a little bit more complex. So we recommend to use an statistical software for that matter, and we're not gonna go into that particular case in this video. I have an example so that we can relate the concept with a practical problem. It reads as follows: a cement company wants to test the effect of fly ash concentration at 22% versus 16% in cement compressive strength, which is measured at 7 days. Assuming a significant level of 5%, so they're giving us the alpha there in a power of 90%. So we know that beta is 10% given this statement. Also assuming a standard deviation of 2.7 megapascal, that's how compressive strength is measured in megapascal. And it is equal for both fly ash concentrations, so they're telling us that we have a case of equal variances. They're requiring us to estimate the sample size needed to detect a difference of at least 1 standard deviation in 7-day compressive strength. So this comment here, at least 1 standard deviation, this is our delta, and our delta is then the same as the standard deviation, 2.7. So sigma and delta are the same. If you remember, delta is basically this, mu minus mu 0. So this is 2.7 according to our problem. So let's see how we solve this using the formula first. So I have a web page, an Excel page here open, and the first thing that we need to calculate is this term right here. Now I'm gonna go toggling back and forth between the PowerPoint and Excel just to show you how I go about this. So you can see that the formula is asking me to calculate the zeta of alpha of half of alpha plus the zeta of the beta. And this term is going to be squared, then we need to multiply this times sigma squared and then divide by delta squared. So immediately we know that sigma squared and delta squared are 2.7. So they are going to cancel out each other out, but I'm going to keep them in the formula. So let's go about doing that. In Excel, this is actually very simple. We're going to leverage some of the functions that exist, and zeta is actually the inverse. So we're going to put the norm inverse. We're going to give it the probability. So we want to know what is accumulated up to 1 minus that zeta value. So this is going to be 0.975. And the mean here is not the means we're working with. These are the means of the standard normal. So the mean of the standard normal is always 0, and the standard deviation of the standard normal is always 1. So that's going to give us the value of 1.96. That is a very typical value for this zeta here. The other zeta that we need to calculate is the zeta of 0.1, and we're going to use the same exact formula in Excel, norm of the inverse. And the probability is going to be the power of our test, which is 0.9, 1 minus beta. Beta is 10%. The mean again is the standard normal, 0 and 1. And that is our value right here. And we know sigma, the problem gave us that, and we know the delta. So n, according to the formula, is 2 times, we're going to open up parentheses, the sum of this plus the sum of this. And this value is actually square. And we multiply this times sigma. And then sigma is also square. We're going to close our parentheses to indicate Excel that that belongs to the numerator. And then we're going to divide by the delta. And this delta is also square. So in short, this is the formula that I just wrote in Excel. Now we're going to hit enter, and that is our sample size, 21.01. Typically when I see a little bit more than the 21, I go above that required. So you can use 21, you can use 21, and this is using the formula. The second method is using the operating curve. So I have copied the operating curve here. Perhaps I could expand this so that we can see it a little bit better. And to be able to use this, I need to know what D is. The values plotted here are the values of D. And D has a very specific formula. We can see it here is the actual difference, which we know is 2.7, divided by sigma, which we also know that is 2.7. So immediately we know that D is going to be 0.5. But we're just going to do it here for the purpose of educating you. So it is going to be this divided, and then we're going to just open a parenthesis to make sure that Excel understands this, by the sigma. And as I type that, we get the value of 0.5. So this is 1, and this is 0, so this has to be 0.5. Now I need to find the intersection between 0.5 and my beta. Beta is 10%. We can see it here. So in this case, my beta is going to be somewhere between, so we can see beta over here. And if I draw a line, so let's draw a line here. So if I draw a line about here, we can see that it touches the curve of 50, which is this curve right here, and it touches the curve of 40. So our value is between 50 and 40, and that's what I call the NC for this case. So let's settle with something in the middle between 50 and 40. Let's say 45. Now 45 is the operating n, the n that comes from the operating curve. The actual n is found through this formula here. So this is 45. We need to add 1 and divide by 2. So we know it's about 23. So we're going to use this value. So we're going to use 45 at 1. And this is our numerator. And we're going to divide that by 2. So this is slightly higher. It's according to the operating curve, it's recommending an n of 23. And this is the minimum sample size per population. So you're going to have to collect, if I go back to the problem statement, you're going to have to collect 23 values of compressive strength using a fly ash concentration of 22% and 23 values of compressive strength using a 16% concentration of fly ash to to be able to have this power or the beta of 10% in this alpha. Now these are the two methods, very simple. The third method, if you have in a statistical software, here I have an example of using Minitab to retrieve this. You can see it shows the sample size to also be 23 if you want to calculate a difference of 27. So the way you set this up in Minitab, you will go to the Stat menu, Power and Sample Size. You will come here to the 2 sample T, click, and I have already set up these values. So I'm going to leave this blank, and the difference I'm going to put 2.7 right here. My power is going to be 0.9, and my standard deviation again is 2.7. And once I hit OK, it calculates my recommended sample size. Here it gives me a summary. This is for a 2 sample t-test. It's testing whether the means are equal versus not equal, and is assuming an alpha 5%. The standard deviation is 2.7, and you can read here that the sample size is for each group. So it's recommending 23. The difference is 2.7. The power is 0.9. That means my beta is 10%, but the actual power is a little bit higher according to the calculations in Minitab. It also gives me this very nice curve where you can see the difference. So it's 2.7. It goes here, and this is my power, which is about 0.9, and the recommended sample size is 23. And these are the three methods by which you can calculate the sample size for the 2 sample t-test using alpha, beta, the difference, the minimum difference that you want to be able to detect, and the equal variance method. So I hope you enjoy our video. Don't forget to join for future videos. This is Jorge Rodriguez with lean6sigma.net. Thanks for watching.